The 2011 earthquake and tsunami devastated parts of coastal Japan. Thousands of people died, houses and homes were destroyed, and the cleanup efforts took months and even years. The impact of the tsunami is still visible throughout the affected areas of Japan, even today. And tonight we'd like to reflect on what we've learned in the last 5 years. We started tonight's program by screening the National Film Board's short film, Debris. You can stream this beautiful film for free from March 10th to 13th by visiting nfb.ca. We're very fortunate, as you guys have seen, to have the filmmaker John Bolton here tonight, and he will answer more questions in our panel later, along with our other guests, Dr. Jay Cullen and Dr. Catherine Clark-Murray. So if you have questions during the coming presentations, we ask that you save them for the panel discussion. Our full name is the Vancouver Aquarium Marine Science Centre, and we always start with the science. So I'd like to introduce our first speaker for tonight, Dr. Jay Cullen, a chemical oceanographer at the University of Victoria. Dr. Cullen has been leading a citizen science project that's monitoring radioactivity from Fukushima. Welcome, Dr. Cullen.
Thanks for that introduction, Kate, and thank you for being here this evening. The same ocean currents that brought the debris that we saw in the last film to our shores are also bringing radioactive contamination from the meltdowns that occurred at the Fukushima Daiichi nuclear power plant as a result of the disaster that happened about 5 years ago. And I'm an oceanographer, I'm a marine chemist, and the reason I'm interested in this problem primarily is that I live here in British Columbia and I'm down current, and I want to know what the impact of this disaster will be on our environment and on our public health. But the Fukushima Daiichi nuclear disaster is very fundamentally a marine disaster, insofar as the vast majority of the artificial radionuclides, this ionizing radiation that was released from the site, ended up in the North Pacific Ocean. And in a very similar way to how one can use markings on debris that washes up on the shore, or the architectural style and craftsmanship of beams that wash ashore, and we can identify these as being from Japan and affecting us here in North America, we can use analytical tools and chemical tools to identify the contamination in no uncertain terms that comes from Fukushima and how it might be impacting both, again, the health of our oceans and public health. And what I'm going to talk to you about today is a project I'm involved with whose aim is to determine what the environmental and public health impacts are of the Fukushima Daiichi disaster for us here in Canada. So the INFORM project stands for the Integrated Fukushima Ocean Radionuclide Monitoring Network. So it's a network of government, academics, non-governmental organizations, and citizen science volunteers whose task it is, who's been funded by a network of centers of excellence called MEOPAR, that's at Dalhousie University in Halifax, to conduct this radiological health impact assessment. We're funded by MEOPAR through to 2017, and this is the period of time when we expect levels of ocean-borne contamination from the disaster to be at their highest levels, and therefore the impact to be most significant, and that's the time period over which we'll be operating on. This diagram shows the academic partners, University of Ottawa, in addition to the University of Victoria, where I work, partners at the University of British Columbia here in town. We have international partners, the Woods Hole Oceanographic Institution, Dr. Ken Bissler, who works with us. Fisheries and Oceans Canada, as well as Health Canada, are involved. This program is really, the INFORM project is leveraging the really high quality, world-class monitoring efforts that have been going on and being conducted by both of these government agencies since the disaster began in 2011. The citizen science portion of the project really wouldn't be possible without the cooperation and effort of our NGO partners, Georgia Strait Alliance, Living Oceans, Rain Coast Education Society, David Suzuki Foundation, the Clayoquot Biosphere Trust, and Surfrider. They help us to reach out to and coordinate our volunteers who collect samples for us, and in certain cases actually go out and conduct the sampling for us at various locations on the coast. And I'll come back to that. But I just can't say enough about how important non-governmental organizations are in terms of reaching out to the public, people who are passionate about the ocean's health. I would, on my own, not be capable of carrying out this project the way it's been carried out without their partnership and their help. So our project is organized with two main observational components. We're making measurements of this contamination offshore in seawater by using research vessels that go out into the Northeast Pacific and into the Canadian Arctic Ocean. We have our volunteers who are collecting seawater samples up and down the coast and sending them back to us to be analyzed to look for contamination. We're also making measurements of the marine biota. Specifically, we're looking at species of Pacific salmon who tend to spend more time in the Western Pacific or farther west in the Pacific to see how much contamination they have and what sort of risk and exposure that leads to in public who rely on salmon for their livelihood, for example. We also conduct an education and outreach component, talks like this, online data portals where the information and data that we gather, we try to get to the public as quickly as possible. Again, there's a real demand for this quality, scientifically derived information about the Fukushima disaster, and that's one of our major roles, is getting that information to the public so that people can make informed decisions about what risk they're exposing themselves to and what's acceptable in terms of the safety for themselves and their families. So I want to go through quite briefly what we're finding. So what we're looking at here is results from seawater sampling conducted offshore. You can see the location where surface seawater samples have been gathered. We have a scale of 0 to 12 becquerels per meter cubed. Becquerel is a unit that we use to count the amount of ionizing radiation in a sample, and cesium-137 is an artificial radionuclide that has been released from Fukushima and is most likely to represent health risks to individuals living in North America, mostly from the consumption of seafood. And so what we see between 2014 and 2015 is the arrival of the heart of this plume of contamination, the very large input of contamination from the reactor site in 2011 being transported by ocean currents and arriving offshore. We see between 2014 and 2015, we see this area of surface ocean where we can see this Fukushima-derived contamination and the prevailing currents that are bringing it towards our coastal waters. Before the Fukushima disaster occurred, there was vestige or a background of about 1.5 becquerels per meter cubed that was present, more or less distributed across the entire Northeast Pacific from weapons testing in the atmosphere in the last century. So anything above that, we were able to identify Fukushima as the source of that contamination. And I'll give some perspective on these numbers in a moment, but in terms of safety, our drinking water standard is roughly 10,000 of these units, the maximum allowable concentration of these radionuclides, where the consumption of that water is not known to cause negative health impacts. So these levels are very, very low, and it's actually quite difficult for us to detect them. These levels aren't something that you can pick up with a Geiger counter. But we do see, and we can document the arrival of this contamination along our coast. And what I'll show you next are results that we're getting right at the beach from our citizen science volunteers. This next figure puts the offshore numbers in perspective. What we see here is this activity of cesium-137 in seawater going back to the height of atmospheric weapons testing at the end of the 1950s. You see that in the North Pacific, we had on the order of 100 becquerels per meter cubed. This is a log scale. And over time, both from the decay of the isotope and also mixing of the isotope out of surface waters, we see those activities are dropping over time. We see a little blip associated with the Chernobyl accident in 1986 and continuing to fall off up into the time of the Fukushima disaster. These are the levels roughly that we're measuring offshore, the maximum activities that we've detected from Fukushima, which you can see is similar to the sorts of levels we had in the 80s and 90s. So this level of contamination that we see from Fukushima is lower than the sort of values that we saw, again, when our species decided it was a good idea to detonate these weapons in the open atmosphere. I pointed out before, we do have a team of dedicated and passionate citizen scientists who are volunteering to help us out for this monitoring effort. We have roughly 15 communities up and down the coast of British Columbia where our volunteers go out to the beach every month and collect a seawater sample that they then return to us for analysis in the laboratory. This is Megan Ives, who lives up in Sandspit and Haida Gwaii. Surf rider here on Vancouver Island, goes out to Port Renfrew for us after catching some waves. They do a little bit of science for us and they send it back to us. Again, I can't stress enough how important their efforts are to helping us understand when and how much contamination we actually see in coastal waters and at the beach. What we found so far over the first year of monitoring, this is a figure showing again the activity of cesium-137, one of these artificial radionuclides from Fukushima that we have to be cognizant of and thinking of in terms of health impacts. And what we're seeing here is a gradual increase of cesium-137 with error given the large space over which we're making these measurements up and down the coast of BC. But we see a general increasing trend that is related to this offshore contamination that we can see by looking over the horizon going far offshore. It's starting to arrive along our coast. We see a couple of points where we unequivocally see Fukushima contamination at Ucluelet at different points that lead to these higher values, but we see this general increasing trend. To put these numbers in perspective again, how much are we actually measuring? This is a log scale figure, and again, what we're showing here is this drinking water standard maximum allowable concentration across the top, this 10,000 becquerels per meter cubed. These are roughly the sorts of values that we saw at the height of weapons testing. This is the highest value that we see offshore that we might expect to reach the coast at some point in the future, and this is the trend that we see thus far. So again, these levels are real. We can measure them. By measuring fingerprint isotopes related to Fukushima, we can attribute some of this contamination to Fukushima, but the levels themselves are really quite low, and they're much lower than levels that we know cause health problems, either from drinking the water, which of course we don't drink seawater, but it's the levels in the seawater which ultimately fix how much ends up in the marine ecosystem, in the marine food web, and ultimately what ends up in fish that humans consume. Another part of our project is looking at how much contamination we can see in the marine biota. And we've been focusing on Pacific salmon, principally sockeye salmon, but also steelhead trout. Because these species, what we know of their life history is they tend to spend more time in the western part or further west in the Pacific, closer to the higher levels of contamination close to Japan. And they pick up this contamination either through the food that they eat or from the seawater in which they swim. And so over the last 2 years, we've collected on the order of about 260, heading towards 300 fish. This last year, 2015, to about 15 streams and rivers, the returning fish were collected with the help of Mark Trudell at DFO, and these fish were processed in collaboration with First Nations communities up and down the coast and analyzed for these artificial radionuclides. We also measure them for naturally occurring isotopes that are always present in the fish and which lead to an exposure of ionizing radiation that, as it accumulates, leads to more or increased risks of health problems. So we measure the naturally occurring radionuclides so we know what the contribution of the disaster is to the total amount of ionizing radiation that you're always exposed to when you consume fish. So what we found thus far, to summarize really briefly, is that between 2014 and 2015, we have yet to see a measurable increase in the amount of artificial radionuclides that we see in fish returning to our waters. In 2015, we were unable to detect cesium-134, which I won't go into except to say that because it has a relatively short half-life, if we can detect it in a sample, we know that Fukushima has affected that sample. Because we can't detect 134 in the fish, it means that it's difficult for us, or we can't unequivocally state that that fish has been affected by Fukushima contamination. What we are able to detect in the fish is 137 cesium that's likely from these previous activities, human activities of weapons testing. And the levels that we're able to detect in the fish are a very small fraction of the radiation exposure that one gets from naturally occurring isotopes in the fish. So in a very measurable way, the total amount of ionizing radiation that you're exposed to by consuming fish hasn't changed as far as we can detect with our very sensitive instruments from before the Fukushima disaster till now. We fully expect that as this contamination comes inshore and is more present in the Northeast Pacific where these fish grow up, that we will be detecting Fukushima contamination in these fish as we go forward, but as of yet, we have not. Neither the 137 cesium that we can detect in these fish nor the naturally occurring isotopes are at levels where we know that health impacts are likely to occur. So the risk associated with eating these fish to one's health is so small as to be unremarkable. So that's where I'll stop for today. For those of you who are interested in the project and the results coming from the project, our project website is a clearinghouse of information derived by the project, but also from peer-reviewed scientific literature about the impacts of the disaster on the North Pacific. We tweet about what we're doing, and you can also follow what we're up to at the University of Victoria. Thanks very much.
Thanks, Jay. Just a reminder, you'll have a chance for questions at the end of Catherine's talk. So I'd now like to invite our second speaker, Dr. Catherine Clark-Murray, a marine ecologist and visiting scientist with the North Pacific Marine Science Organisation, or PICES. Dr. Murray has been studying marine debris generated by the tsunami. Welcome, Dr. Murray.
Thanks, everybody. Thanks, Kate, and a special thank you to the aquarium for putting on the event tonight. It's a real pleasure to be here. So as we saw in the film and as we just heard from Jay, this field of debris was washed into the ocean and made its way across to our shores in North America and also to Hawaii. And right away there was concerns, especially from a navigation standpoint, that ships or boats might run into some of this debris. But one of the other concerns didn't become apparent until a specific piece of debris landed on the shore in Oregon. This is a 20-meter-long floating dock. It weighs 188 tons. It came all the way from the affected region of the tsunami and landed in Agate Beach, Oregon. And growing on it was this amazing diversity of species, animals and plants. Things you might recognize, these are mussels, and this is kelp, and a bunch of other things there that, that we see typically in ports and marinas around the world. Anything that spends a lot of time in the water accumulates this kind of community. And so scientists right away in the area were concerned and were called out, especially scientists from Oregon State University responded. And so they came out and took samples of these things and spent months and months identifying them to see what exactly was on the dock. And at the end of their work, they identified 125 species, many of which are from Japan. So because of the concern that these are species that are originally from Japan, many of them are not present in North American waters, Oregon Parks and Recreation responded, and they spent some weeks and months cleaning and scraping and burning the material off, and then finally burying it above the high tide line so that it couldn't escape into the natural system. So this dock originated in the port of Massawa in the affected region from the tsunami. This is a picture from 2008 when these were brand new, shiny, unsinkable docks. The picture from Google Earth on the right here shows all 4 of them missing after the tsunami. So we know where one of them went. We found it in Oregon. A second one, up here on the left, was spotted by fishermen off the coast of Maui in the Hawaiian Islands. The fishermen even climbed aboard, probably to take a selfie. They spent 2 days fishing off of it, using it as a fish aggregation device, so they were hauling mahi-mahi off it. When they were done fishing, they called the authorities to let them know where it was. By the time the Coast Guard got there, it was gone, and they couldn't find it again. This is a third dock on my right here. This landed in December 2012 in Washington State at Grays Harbor. It's physically impossible for these to be the same dock. They just can't move fast enough to get from Hawaii back to Washington State. So this is a third dock. This is in a more remote location, but scientists again responded and took samples, and they identified another 63 species attached to this dock. So the concern has been around invasive species, and in the title of the talk we said alien species. And alien species are introduced, they're non-native, there's a lot of terms for them. It just means something that originated in Japan in this case and is not native in North America or Hawaii. So this is something new, it didn't evolve here. And sometimes, in a very rare case, alien or introduced species can become invasive species. And this is a term that we only use when the species has established and spread and then has some noticeable significant impact, either on the communities living there, on the ecosystem, or on our economy. And this is a picture of a good friend, Jim Carlton, and he's an invasive species ecologist. He's been leading the charge on this for the past 4 years. He will try and respond to any tsunami debris item that comes in to try and get samples of it. He's talked to Pete Clarkson a lot about this yet. And so in response to this concern about potentially invasive species, the Ministry of the Environment of Japan funded a research project through PICES that I work for. PICES is the North Pacific Marine Science Organization. And so PICES, with Jim Carlton and a number of other scientists, has convened a project research team, and they're looking at all different aspects of the risk from tsunami debris, mostly in terms of these potentially invasive species. They come from 16 different institutions, and a few more are added every year. We're coming up on the 3rd and last year of the project. And so with Jim and all of the other members of the research team, they have sampled more than 400 debris items from Alaska and British Columbia through to Hawaii. So we've seen a lot of these items now in the film. Some of them you might recognize from media, so things like derelict boats. There was hundreds of these smaller skiffs that washed up all over the place. I know Kate's seen them. This is a picture of that same post and beam lumber that you saw in the film. And then there's a host of all those other things that Pete had in his yard, things like buoys and crates and pallets, all those kinds of things. And what our team was interested in is when it looked like this, when there was something living on it. And so you might be thinking, okay, what's the difference between something from the tsunami and from general marine debris that you would see from, dropped anywhere in the North Pacific? Oh, sorry. Let me go back. So from these 400 items, they've identified 332 Japanese species. So some of these things are things you'd be very familiar with. They're bivalves like clams and mussels. There's crabs and worms on them. Some of them are things that only a couple people in the world could ever tell apart. So we leave it to them on those scores. So getting back to that question of the difference between tsunami debris and general debris, as you saw in the film, and Pete pointed out, things that spend a lot of time in the open ocean have these distinctive open ocean species. So those are goose barnacles. In the background is, hopefully you can see it, there are these encrusting organisms called bryozoans. And up close they're quite pretty. They look almost like lace. But these two species are only found in the open ocean. So when we see a piece of debris with these kinds of species on it, this is our general marine debris. It's probably not from the tsunami. But what's interesting about tsunami debris is this amazing diversity of species that are attached. So just in the bryozoans, these kind of lacy organisms, there's 57 different Japanese bryozoans, and these are coastal species that made it all the way across the Pacific Ocean to land in North America and Hawaii. We even saw Japanese sea stars. This one on the top is Asterias amurensis. It's actually become an invasive species in other parts of the world. Australia is struggling to eradicate it now. In some of this post and beam lumber, scientists have drilled through those and looked at the shipworms. Shipworms is a really strange organism that has been the bane of wooden ship owners for thousands of years. It's actually a tiny bivalve that eats its way through the wood and creates these long burrows. But in the tsunami debris wood itself, they have identified 6 species of shipworm, some of which we do not have in North America or Hawaii, and a couple of these species have invasion histories elsewhere. They've also identified more than 70 different marine algae species. This one on the top is the Kelpondaria pinnatifida. It's also been known to invade other places of the world, like New Zealand and Australia. We do not currently have it in British Columbia. And there's some interesting findings about parasites and pathogens of concern. So this is a tiny hydroid. You can think of it as a tiny sea anemone. And scientists at the Smithsonian found this within mussels growing on the tsunami debris. This parasite is widespread in Japan. It's not in North America. So there is concern that if this were to be introduced in North America, that there could be impacts on the shellfish aquaculture industry. So your next question is probably, well, have we seen any of these things establishing and spreading in our waters? And the answer is that we are looking through the Pisces project. We've been doing field surveys, various sites in North America and Hawaii. We've been getting mussel samples and collaborating with a bunch of different people to get mussels from up and down the coast of North America to look for these parasites and pathogens. And we've also been doing fouling panel studies. Fouling panels, we just stick a piece of plastic in the water and pull it up 3 months later and see what's growing on it, to see if any of those are potential tsunami debris species. So there's only been one possible, and I will stress that word, possible introduction detected. This is the striped knifejaw fish. A small number of individuals were found in 2 different boats that washed up on the shore of North America. The boats were sitting kind of tilted in the water, and the submerged surfaces at the back were acting kind of like an aquarium, and the fish were quite happily living in the back here. And then a few months later, a fisherman pulled a crab trap up and had one of these in it. So right now we don't know if there's an established population of these or if it was a coincidence. These are also in the aquarium trade, so it's hard to tell, but this is my only possible introduction at this point. So given that this is a really interesting research opportunity for us and everybody's very curious about the potential risk from invasive species, I will also point out that we have a number of sources of invasive species. Just here in Vancouver and the Strait of Georgia, there's almost 150 invasive or introduced species, I will say, to our waters. Some of them date back to early imports of oysters for aquaculture. Some of them have come in with ballast water in our commercial ships or on the hulls of our commercial ships or recreational boats. And some of you might have remembered the uproar about the Burnaby Pond snakehead fish. So this was the single fish, and we linked it back to probably an aquarium owner who didn't want to sacrifice his pet and released it into the pond. So While the tsunami debris might have brought these things over to us, I would like to say that it's probably a very small source of invasive species compared to these things ongoing now. So, thank you.
Thank you very much, Dr. Murray. I'd now like to invite Dr. Cullen, Dr. Murray and John Bolton up to our panel table here. And I'd like to encourage any of you in the audience with a question to raise your hand and we will bring the microphone to you. So I'm just going to start with a question for you guys while everyone's thinking of their questions in the audience here. I'd like to ask each of you in turn, what's the most important thing you've learned since the tsunami through your work? And John, maybe we can start with you, the microphone in the middle there. Just check that's on.
The most important thing I've learned. Before I answer that, I have to acknowledge that this is really fun for me to be here tonight because it was in late 2013 that I came to an event much like this one, and Pete was speaking with two scientists. So there were two doctors and a mister, just like tonight. And he gave a presentation about his work, and I introduced myself to him after and said that he seemed like someone I'd like to make a film with and a film about, and we kept in touch. And it was throughout 2014 that we shot the film and then finished it in 2015. So it's really, this is full circle for sure. It's fun. So thanks to the aquarium times too. I guess the most important thing that I learned, and I learned this over the making of the film, and maybe in hindsight it's obvious, but you know, these stories of these lost and found objects. You talked about the how some of them we might have heard in the media and the docs and the motorcycle and other things. I mean, they're kind of, it's just irresistible. It's like a message in a bottle. It's trying to, you know, when you can reunite something with someone, then the person who found it and the person who lost it have these connections. And I knew the first time I got to go up to Tofino to spend time with Pete and to start working on the film, I noticed, and it's in the film, the first thing you see when you get to Tofino is all the tsunami hazard zone warning signs. And you know, as I got to know Pete, I knew he was doing an interesting project. As a filmmaker, you want to make a film about what he's doing, but I was more interested in why. And you know, it became clear to me that as I got to know him, when he looks at these house timbers, he thinks of his house and he thinks of his home and he thinks of his family, and that these same forces that brought these objects to him, you know, the same forces that caused that earthquake and tsunami are the same forces that that we're vulnerable to in this part of the world. So they become kind of a visible, almost like little totems of those forces and that power. And so if anything, it made me more aware of that. And I said earlier that the film and the memorial were kind of like the same project, and I felt like we both wanted to pay our respects, but also create pieces that served as warnings of sorts, as far as our own preparedness, however you want to take, however you want to, in all the different ways that what the word preparedness can mean. So yeah, that's for me kind of on a less scientific and more personal note. It really made me think about the precariousness, you know, of all life and of all circumstances, but also in this part of the world as it relates to that.
Catherine, do you have a thought on what you've learned since the tsunami? Since
I began working on the project, I think I think I've been struck a number of times by what we thought we knew about what went on in the open ocean as scientists and as ecologists. And then this rare event has really challenged a lot of our traditional theories. For a long time, we thought that the open ocean was this very kind of barren place, that not a lot survived there, especially for coastal ecologists. We're used to going out to the shore and seeing lots of amazing diversity, and we thought that that couldn't really happen in the open ocean. And then we see these pieces come across, and there's 125 species, and they've been doing quite well for 2 years, 3 years, 4 years. I mean, they've been, if you had asked us 5 years ago how long we thought coastal species could survive at sea, we would have not said 5 years. So we've learned a lot of interesting things, and it's been quite an honor to be part of that research.
And Jay?
I've been quite impressed and inspired by members of the public and their passion for the health of the ocean ecosystem, and how ready people are to roll up their sleeves and help in the scientific process and the process of discovery when given an opportunity. So I've been reassured and actually, yes, inspired is the word by how strongly people feel about ocean health. And you're not always exposed to that day to day working in the laboratory. And so I've found that to be a very valuable lesson for me.
Thank you. Do we have a question in the audience here? Jonathan's going to come over with the microphone.
This question is for Dr. Murray. I'm just curious if you have a field guide of the invasive species you've been studying, because we go out in the field and we've seen, and I've seen some of what you've been talking about, but it would be great to be able to take that field guide out and be able to identify species as we're out there.
Absolutely, that's a great question. One of the things that we're working on is a field guide, and we're hoping to have one specific to the different regions, because the things that you would look out for in Hawaii would be very different than the things you would look out for here in British Columbia. So it's early days for us. The taxonomists, the ones who like to tell apart those tiny bryozoans, are still working on making that final list, and then absolutely we are hoping to have a field guide out by the end of this year. Thank you.
Yeah, I got kind of a multifaceted question. A lot of the work that you do relies on data acquisition and knowing where to place your resources. Has there ever been an interest in kind of like a nationally accessible database of like topographical maps to show in like high resolution where the key areas are that need to be looked at?
Can I ask you a question back?
Certainly.
In areas to look at, are you thinking of for invasive species?
Well, areas
for debris cleanup, for radiation monitoring?
For all aspects of environmental study. Like a lot of it would be to do with tsunami debris and the invasive species that it brings in. Has there been an interest in creating a database and mapping all these areas?
So one of the pieces that Pisces and with the Ministry of Environment funding we've been working on is we helped fund some aerial surveys of British Columbia and also of Hawaii. We felt that we didn't know a lot about that exposed coastline. And so those maps we've been working with Kate at the aquarium and also with the BC government, and those are in the process of being made public. So they are going to have maps, especially to help people who are interested in targeting those areas where a lot of debris accumulates. So not just tsunami debris, just general marine debris, and so that we could target our resources more effectively.
So there's already a large amount of aerial mapping being done?
We did some for this project, yes, and there's some older pieces, yeah.
Great. So if we have another question here, Jonathan?
We actually have an online question, so I'd like to go ahead and read that real quick. This is from Bruce. What invasives what invasives should we be most concerned about here in British Columbia?
They're all for you, Catherine.
You got the good stuff. A few off the top of the head. I showed a picture at the start of the doc with the kelp on it, Undaria. So that is one that we don't currently have in British Columbia and has been invading, moving northward from California. So that is one that I would definitely be interested in keeping an eye on. The starfish that I showed, Asterius, is also one that we would be very concerned about if we saw here. There was a small number, maybe a dozen or so, that we've seen altogether that have made it on, you know, the world's worst invaders lists around the world. So there's a smaller number of those which we would put on a watch list for everywhere, and so we hope to have that out soon.
Hi, there was a graphic in one of the presentations that seemed to show ocean currents, I think. I'm wondering if we know if the radiation is widely dispersed or is it concentrated in one area?
So the question was about whether or not we expect concentrated spots of higher radioactivity. That really depends on the chemistry of those elements rather than whether they're radioactive or not. So cesium, which I talked about, strontium, which I didn't spend much time talking about today, but which is a concern, those are elements that behave, that are salts. And so they're dissolved in the ocean water, and they tend to follow the currents themselves. So the horizontal and vertical mixing that homogenizes salt in the ocean is also acting on those isotopes. So both diffusion and mixing are acting to homogenize them. And so we see less concentrated pockets of those because of their chemistry, the way they behave. Other elements that tend to stick to particles, for example, are going to be dominated by that association, and so there are elements that are quite concentrated in the sediments close to Fukushima. And then, of course, elements that tend to bioconcentrate, that are taken up by organisms, or their pathway through the environment is going to be affected by those pathways. But the ones that we're primarily interested in, because of the large amounts that were released and their potential to cause harm, they tend to be dissolved in ocean water, much like salts. And so we see less of that sort of hot spot behavior or aggregation.
Hi, thank you for all your talk so far. I have a question for both of the doctors. I'm an artist myself, and I'm curious what you two think about the power of art showing these disasters, and how you think we could do a better job of displaying the severity of them, or you know, really telling people what has happened. Yeah.
First. I was really pleased to see the film. We just returned from a trip to Japan a week ago, and we were at the Tohoku region. And to see it in person, they're still rebuilding 5 years after. To see it in person really speaks to you in the heart. And as scientists, that's really difficult for us. So, I mean, we just don't do a good job at it. I can show you species lists and pictures, and that's about it. So we really need art and artists to speak to the heart for us, and to really communicate, because while there's a lot of really interesting scientific questions, this was really a human story and a human disaster, and it's hard to keep that in mind, but I think it's really important. So.
I would say, too, that artists and visualization of data and conveying sometimes complicated scientific findings or ideas or concepts visually can be a really powerful tool, and makes the scientific process and the results of scientific inquiry more accessible. And that's something that, again, I think sometimes as scientists we're not trained as well in conveying information in a way that's universally acceptable. And both visually presenting data, audio data, people who can't see, for example, there are some really powerful techniques for conveying what's wonderful about science and what's wonderful about the world that we learn through using science as a tool. And I think that artists have a lot to contribute in that line.
That's a great question. I think we've probably got time for one more question up here.
This question is for Jay. I was wondering about your results with respect isotope accumulation in shellfish, since there's filter feeders. Did you see anything interesting, and do you expect any accumulation to increase in the next couple of years?
So the question is about bioaccumulation, bioconcentration. There are solid studies that have been done looking at how different organisms, whether they be algae or shellfish, mollusks, vertebrates like fish, how they accumulate radioisotopes from the environment. One thing that we wanted to start initially with the project was looking at salmon, because they are so culturally and economically important. This year we're going to start looking at scallops, partly because one of the reasons why we're looking at salmon is to hopefully learn something about how salmon spend their time in the Northeast Pacific. We might find out where they're feeding, where they're spending more time, but they move, and that's complicated. Having sentinel species like shellfish that spend their whole lives in one spot, they should be useful for helping us to monitor this contamination. So the short answer is that we're going to start looking at scallops beginning this year. And the organisms do concentrate the isotopes from the seawater in which they grow. The level to which they do is species dependent, and based on what we're seeing in seawater, we don't have any grave concerns about what we will see in organisms that live in our coastal waters here. But that's definitely on our radar.
I've got one more question down the front here.
Hi, this question's for Dr. Cullen. I was quite taken by your graph of the levels of acceptability, and a couple of things struck me there. Your limit of 10 at the top, 10,000 units. From what I understand, the acceptable amount in Japan was a lot lower. Now, when was that level set? Because I understood that it was raised since Fukushima. That's one of my questions. The second one is, as you notice on that graph, the 1960s, where they did the nuclear stuff, the outflow of that, 50 years on, we now know that many, many, many more people are getting cancers. I mean, it's sort of like 1 in 5 or 1 in 3 can expect to get some form of it nowadays. Now that's 50 years later, and even though those limits are, you know, in the middle, and we're not anywhere near that, there's still some kind of concern that this amount that's just coming in now, like that big patch, hasn't arrived yet. So what you're expressing today is good news up to this point. So do you see further to this in the future that when this big patch arrives, these levels would increase, that we might start to near those levels of the 60s? And where did that put that limit at that time? And also, as a final question, when Fukushima happened, I had heard at the time that Canada had shut down its radiation monitoring stations. Is that reversed now, or why did they do that at that time?
I'll begin with your last question. So very briefly, Health Canada, the Canadian government, did not shut down any radiation monitoring stations in the country. We have comprehensive test ban treaty monitoring sites and also point source sites that Health Canada is always making measurements to look for ionizing radiation in the environment. In fact, after the disaster, my colleagues at Health Canada actually increased the frequency with which they were making measurements. So they went into crisis mode because it was an event and they needed to know what the risk would be to the public. And to do so, they did fantastic work. Unfortunately, at the time, they weren't able or could not communicate directly what they were doing. And I think that's unfortunate because it was world-class monitoring that they did. So that's a bit of misinformation that you'll hear, that they shut things down, and that's just not true. What was being reported on is that they returned to their regular frequency of monitoring a few months after the disaster, once the atmospheric levels had dropped back to what was pre-Fukushima background. The first part of your question dealt with how maximum allowable concentrations are derived. When it comes to Japan, after the disaster, they actually made their levels more stringent. Okay? They didn't raise them, they actually lowered them. Now, in Canada, the maximum allowable concentrations we have for drinking water, for example, have been around for at least 40 years from what I could find. Going back on the web, you find 1996, 1994, and they predate the memory of anybody, my colleagues directly at Health Canada. So at the same level, they have not been raised. That's another bit of misinformation. Those levels are derived, and this highlights a problem with these levels in that they seem somewhat arbitrary if a country simply decides to lower theirs. So how could it have been safe at 500, but now you're telling us that 100 is the maximum allowable concentration? So that's something, what happened in Japan in 2011. They said, now we're going to make them more stringent. Well, was it unsafe before? And the short answer to that is different countries have different levels. Those levels are calculated based on, for drinking water, for example, assuming a certain amount of water that people consume per day and how much ionizing radiation they receive from that over the course of a year. And whether that leads to a dose in accumulation that translates into real measurable risk that's unacceptable. So that's how those levels are set. And it does highlight the fact that at these very low exposure levels that we see, there's no set level that hard science says this is absolutely unsafe necessarily or absolutely safe. And that's what you see in these different levels in different countries. The second part of your question, I have to admit I've lost track of that now because there was 3 in there. Oh. Yes, so when it comes to cancers, now I'm not a medical doctor, but one of the reasons why more of us are getting cancer and more of us will get cancer is simply because we're living longer than we have in history. Links of ionizing radiation in the environment to cancers, we know the risks of ionizing radiation with respect to developing certain types of cancers very well. Like compared to other contaminants that can cause us problems like heavy metals, we know a lot about ionizing radiation. There's no simple explanation for why one individual gets cancer and one individual doesn't. But at the levels that we're talking about and the levels that we see offshore, the maximum levels that we see, they're not going to get into the ballpark where we would say this is going to be a problem for this species or this part of the ecosystem. Now, we're going to continue to make the measurements because I think it's important to have this information, especially when the perception is that information was not being gathered and not being distributed. And we're going to continue to make those measurements and communicating everything we find as transparently as we can.
Thank you, Jay. I'd like to encourage any of you, if you have further questions, to come down and speak with our panel here at the end. I'm sure they'll be happy to stick around and chat with you guys as well. Can you please join me in thanking our 3 speakers? So the tsunami has shown that all waterways are connected, and I'd love to encourage each of you to take action for your local waterway right here at home by joining the Great Canadian Shoreline Cleanup any time of year, anywhere that land meets water. You can learn more about our program by sticking around and chatting with us afterwards. You can grab a card from the table outside, or you can visit shorelinecleanup.ca. Thank you very much for joining us here tonight. We're going to finish with a 2-minute video about a recent cleanup that we did. I'd just like to remind you the Vancouver Aquarium is a self-supporting non-profit society dedicated to the conservation of marine life. You can learn more or donate at vanaqua.org. And now I'd like to leave you guys with this little video about our latest cleanup. Thank you very much and good night.
It's untouched, wild, an example of nature in its most raw form. Wedged between the endless Pacific Ocean.
I think of trees, beautiful beaches, whales, I've always seen the West Coast Trail as kind of like a challenge, something to conquer and something to experience.
West Coast Trail is truly one of the crown jewels of the Canadian National Park system.
I'm expecting to see a good deal of stuff that's come over from the tsunami in Japan.
I hope we find beautiful, pristine, clean beaches, but I'm pretty sure we're going to find a lot of things that shouldn't be there.
Thanks, guys.
Resilient, they stay around an animal's neck. They look pretty harmless, but we know these ones cause a lot of damage. Oh yeah.
That was